So, hello everyone. Welcome to our first seminar. So, today we have Professor Francisco Pedro. He's a professor at the University of Bologna, and he works on cosmology and string theory. And he will be telling us, he'll be talking about the observables from the early universe. So, yeah, take it away.
Okay, so thank you very much. Thanks for the invitation to take part in this initiative. So, as the title says, I will be talking about observables from the early universe, and this being a GR school, obviously is a subject that has to do with GR, but it also is at the same time a somewhat more advanced topic which requires some knowledge of QFT. Now, what I want to do today is pick up where Luca Brunelli left, I think last week, the last lecture he gave you, and explore a bit more the physics behind cosmic inflation. In particular, what are the observables from this period in the early universe that we can confront, things that can be measured and that can be used to constrain our knowledge or the hypotheses about the universe at very early times. So this is, as I said, a somewhat more advanced topic, and we have limited time. So tough choices have to be made as to what material to present. So we'll see how it goes. I try to keep it as linear as possible, but keep in mind that there are some steps that, due to time constraints, I will not be able to show explicitly. To fill in these gaps, there's a couple of very good references that you can look by yourselves. The first one is an absolute brilliant book by Mukhanov and Vinitsky on the introduction to quantum effects in gravity, and large parts of what I'm saying are based on the material that they present in a similar way that they present. And there's also the various lectures by Daniel Bauman, in particular the Tazi lectures from a while ago, quite a while ago actually, and his recent book. Now, the underlying topic is going to be, as I said, inflation, and in particular, inflation as a solution to the problems of the hot Big Bang, okay, which I will abbreviate as HBB. Luca has told you that the hot Big Bang suffers from severe fine-tuning problems in terms of the initial conditions that are required uh, of the universe in order for it to evolve into something that resembles what we observe today. And that one way of solving these issues is to postulate that at early times there was a period of inflation, and inflation is just at its core a period where there was a shrinking Hubble radius, which is nothing but having a scale factor times Hubble parameter that are growing. Okay? This is what we're trying to achieve in the early universe, a finite period of time where Hubble parameter, so h is a dot over a, so it's the derivative, the time derivative of the scale factor divided by a, and we want this a times h to be growing. Now, there's a number of ways to achieve this. So essentially, we say we fix a theory of gravity, and now we need to supplement this theory of gravity, which we take to be just the Einstein-Hilbert gravity. We supplement it with an energy momentum tensor. So we put it some form of matter that needs to give rise to this behavior for the Hubble radius. Now, the simplest way to do so is to have a minimally coupled scalar with a flat potential. Okay, and the flatness of the potential is an issue for model building, but if the potential is flat, then this sort of dynamics can come out. Now, to be precise, we're dealing with a theory where the action is the Einstein-Hilbert action. So d for x root g r times m Planck squared plus the Klein-Gordon action for the matter sector, which we take to be just a scalar field, minimally coupled with kinetic term and some potential, okay? Like so. Now, it may seem a relatively simple action, just gravity coupled to a scalar field, but in full generality, this is quite a complicated problem to solve in the absence of symmetries, and that requires numerical techniques. So if we don't want to go there, and there are reasons to study this analytically, the simplest assumption we can make is to assume that both the scalar field, which is usually a function of time and of space, and the metric g mu nu, which enters in the Ricci scalar, which is usually a function of time and space, we approximate it by only functions of time. Okay, so depend only on time. Now, if this is the case, things simplify enormously, and we can study the dynamics as Luca showed to you, I'm sure, in his lecture. So the equations of motion that follow from this action are an equation, a Friedmann equation for the Hubble parameter, which is sourced by the scalar field, and an equation of motion. There's another equation, but it's not independent from these. And an equation of motion for the scalar field. Okay? So what happens is that we have a situation where this is the energy density in the scalar field, and the scalar field is essentially behaving as a perfect fluid with an energy density that is kinetic plus potential. Here, this is all phi bars. And the pressure that is kinetic minus potential. Again, phi bar. And the dynamics of the scalar field follows of the homogeneous mode, which is what's usually called this guy here. It's homogeneous because it's independent of the spatial coordinates. It's the same everywhere in space. Now, the equation of motion for the homogeneous mode is essentially that of a body moving in a medium that creates some friction under some external force. And you have a term, this first term, which gives us the acceleration. There's a term that gives us the friction. And then there's this term that gives us the driving force. And in order to have a slowly varying Hubble parameter, or in other words, AH that is growing, we need to induce this system to enter slow roll dynamics or a slow roll regime. And in a slow roll regime, phi is moving at terminal velocity. Okay, so this is essentially the same thing that happens when a skydiver jumps off a plane. They accelerate, accelerate, accelerate until the point where the friction equals the gravitational attraction from Earth. Okay, at that point, the acceleration goes to zero, and there's a balance between the friction and the driving force between these two terms here. Okay, this is essentially what's happening in slow roll dynamics, and in slow roll dynamics, then we have a negligible acceleration. And we have a Hubble parameter then that is essentially sourced 8 pi g over 3 by the potential energy alone. And this is the equation of motion, the approximate equation of motion for the scatter field. Okay, so these are the slow roll equations of motion. Now, this in slow roll, what is happening is we can see it from these two equations without having to write any other quantities. So if the potential is flat, the Hubble parameter, as phi rolls, the value of the potential changes by very little. If the value of the potential changes by very little, then the Hubble parameter changes by very little as well. So in slow roll, h is almost constant. Okay, so the fact that the Hubble parameter changes very little means that I can have an exponentially growing scale factor. Okay, just by integrating h, the definition of h, which is constant, you can show that a goes like e to the h times t. And this is in essence, what makes inflation attractive as a solution to the curvature, homogeneity, and isotropy problems of the hot Big Bang. So what are the predictions then? Okay, what are predictions from inflation? So if inflation happened, what does an old universe look like to an observer living at late times? Well, the universe should be flat, or spatially flat, to be more precise. It should be homogeneous, and it should be isotropic. Okay? All of these things have been checked observationally. Okay? All of these 3 bullet points have been confirmed, and by different probes, but perhaps the most impressive one is the one that you can see here in the background. So this probably is familiar to some of you, but for those who see this for the first time, this is a map of the full sky in terms of the temperature of the electromagnetic radiation that is arriving in different directions. Okay, and even though this looks quite spotty with blue and red dots denoting different temperatures, colder and hotter spots, so lower and higher temperatures respectively, this is actually artificially augmented because the difference between the blue and the red spots is of order 1 part in 10 to the 5. Okay, so what's actually observed is an extraordinarily homogeneous, or extraordinarily isotropic, I should say, temperature map of the sky. So anywhere in any direction you look, the temperature is 2.73 Kelvin. And then if you look at different directions, the difference in temperatures is 1 part in 10 to the 5. Okay, so this is the level of to which we have tested the isotropy of the cosmic microwave background, and by extension, the isotropy of the primordial universe. So the CMB, the cosmic microwave background, plays an enormous role in checking these 3 features of the late universe. Now, the anisotropy, that is the delta t over t mean, is 10 to the minus 4 to 10 to the minus 5 level. Okay? It's absolutely tiny, but nonetheless it's non-zero, and it is a number that we need to explain as well. So is there any other prediction from inflation? Okay, Is there anything else we can learn about the early universe? Um, in particular, can we connect also inflation to this level of anisotropy of the CMB? And it turns out we can, and huge amounts of work have been put into this over the last 30, 40 years, 40, more 40 than 30. Um, And it is related to something that is at the heart also of the formalism of general relativity, which is that of perturbation theory and gauge invariance. Okay, this is a technical subject, super, super interesting, but because of time constraints, I won't be able to go into the details. So I will simplify things a little bit, such that we can get a degree of appreciation for the relation between inflation at early times and this sort of temperature anisotropies that you see here in the background. So the first step that we can take in order to try to connect inflation to the early universe beyond the background level, which is what allows us to explain the flatness, isotropy, and so on, is to go beyond the homogeneous cosmology, which is to say, just do cosmological perturbation theory. Okay? So we won't do this. We will do a simplified version of this. Okay? But the idea is that phi, which is a function of space and time, we will expand this as our friend, the homogeneous mode, plus a perturbation, so delta phi, which is a function of space and time. Okay? And you do the same for the metric. So these are the background, usually referred to as the background, and these are the perturbations. As the name suggests, the perturbations need to be small in some sense. Okay? So for the case of the scalar field, delta phi over phi bar is to be much smaller than 1. And the reason for this is that we want the background solution to be a good solution up to small corrections. And we're going to expand in these small corrections, and this series, if we want to make any significant statement, this series must converge. Okay, we're going to truncate it, and it has to converge. So this is, in essence, what needs to be done. Now, what really happens is that inside delta G mu nu, or inside the metric, there are scalar, vector, and tensor perturbations. And these scalar, vector, and tensor perturbations, the way they appear depends on your coordinate choices, or in what is sometimes called on your gauge choice. And you need to work either with a fixed gauge or with gauge invariant variables. This is an extraordinarily interesting subject, but I will just skip through it and work in a simplified situation where the metric does not have any perturbation, and I'm just going to focus on the perturbations of the scalar field, because this is the sort of the minimal thing I can do to still show you some interesting physics that comes out of inflation beyond the background level. Okay, so we focus on the scalar perturbations and keep metric unperturbed. So let's do exactly what I said. Let's then study the action for the scalar field. Okay? We have a minimally coupled scalar field, which we now assume to be given by a background plus a small perturbation. Okay? me just write this like so for short, minus v, which is phi plus phi bar plus delta phi. Okay? V is some function, because I have inflation in mind. V should be in some sense flat, at least for certain range of the field values, such that I can have a period of inflation in the early universe. And now what we're going to do is, because we're assuming these perturbations to be small, we can expand this whole action in delta phi. So we do a Taylor expand in delta phi to second order. Okay? We can go higher order, things become a bit more complicated. We don't learn anything interesting for the purpose of this talk. But there is a lot of interesting physics, I should say, in the higher order terms that we will neglect here. But for this lecture, let's do as I said. So if we do that, so let me just pull this back. This is already quadratic. So we just do the square of the sum, we expand it, and that's all we have. This is a general function, so we're just going to evaluate, we're going to Taylor expand this as v of phi bar plus derivative of v calculated at phi bar times delta phi plus the second derivative over 2 times delta phi squared, just like a normal Taylor expansion. And if we do so, the action for the scalar field is the action for the background, so the quadratic action, so kinetic minus potential, plus a mixing term, d4x square root of g d phi bar d delta phi. Here I'm assuming, so let me just write it like so, d mu minus v of phi calculated on the background times delta phi. And then, so this is the linear terms, just proportional to one single power of delta phi. All of the terms are like that. And then we have d4x square root of mod g, there's a mod missing here, 1/2 of d delta phi squared minus second derivative calculated in the background, delta phi squared over 2. Okay, so this is what we have. And then we'll have, obviously, or the delta phi cubed terms, which we neglect. Now, what we have here then is a situation where we have the background dynamics being determined by the background action, and the dynamics of the perturbations being determined by this. So S of delta phi fixes dynamics of perturbations. Why is that so? It is so because this term is actually identically 0. And this you can check as an exercise. Okay? You can check that using partial integration and the equations of motion for the background, phi bar, that follow from this term is identically 0. So the perturbations are completely determined and decoupled. So they couple to the background metric, and they determine, and their dynamics is determined by this action. I mean, we can make it more compact by defining the second derivative of the potential calculated at the background, but as the mass of the field of the perturbation. So m squared, and so S of delta phi can be written just as you do in the first course on quantum field theory, quantization. Well, this is just the action for a scalar field, which we will now try to quantize. Okay, so this is the action for the perturbation. So if you have something that is given by a homogeneous field rolling in a flat potential, and you kind of perturb it a bit, you somewhere in your space-time you get the field to be a little bit above the homogeneous value, and this action tells you how this perturbation evolves as time goes on, and how does this perturbation propagate eventually also through space. So it fixes the dynamics of the perturbations. Now we want to study this in in a setup that is amenable for inflation. Okay, so let's just fix the metric. So fix metric to be given like that. Okay, so this is essentially conformally equivalent to flat space. Okay, so this is the metric in Minkowski. And this is the conformal factor given by the squared of the scale factor, and tau is the conformal time, which is just a useful way of parameterizing time, which treats time and space in the same way, in the sense that they scale in the same way with the scale factor. So if we insert this metric in these coordinates into the action, we get the following. A kinetic term scaled by a squared, and then there's the factor of a to the 4 coming from the square root of the metric times m squared delta phi squared. Now, if a here were a constant, any value, just constant, we could pull it outside of the integration, and we would have the action for a scalar field in flat space, okay, and which is something that we can study, quantize, and analyze. Now, that's not the case when you have gravity. So this is the presence, this is gravity here for you. And what we can do is we can be a little bit clever and define a rescaled variable, let's call it chi, which is a rescaled scalar field, which is just a times delta phi. Okay? And if we do so, it's just a matter of taking the derivatives. One can show, so if we define this, one can show that the action now for chi, which is a function of delta phi, is identical or formally identical to that of a scalar field in flat spacetime. Okay, so this is the action for chi, which is just a cousin, a close cousin of delta phi, the perturbation. This is some effective mass squared, defined as m squared a squared minus a double prime over a, and this is formally equivalent to a scalar in flat space. Okay, so if we want to study perturbations around an inflating or quasi de Sitter background, we can just recycle our knowledge regarding scalar fields in flat space, both classical and, as we'll see, also their quantum mechanics. So this fact that this is the same up to the fact that the mass depends on time, okay? Because the mass depends on the scale factor and the scale factor depends on time. So the fact that the mass depends on time, and this dependence on time comes from gravity, okay, means that energy is not conserved. Okay? And it also has some interesting implications for the quantum analysis, let's say, of this system. So if we put that, yep.
There are a few questions in the chat. Would you be willing to take it now or maybe come back?
Sure, sure. Let me, just that I can't see everything at once. So let me try to find them. Where is this Zoom? No,
What is chi prime? One question.
wait a second. Chat. Here we are.
Or I can repeat it for you.
What is chi prime? Chi prime is the conformal time derivative of chi. So by prime, so this is partial, d chi d tau. Then is the action. Yes, the action is the action for the scalar, for the Klein-Gordon scalar, which I've expanded into background plus a perturbation, so plus a delta phi. I think that's it. Yeah, Luca seems to have responded to that. So
Yeah.
yeah,
Thank you.
suppose we can go. Just get that out of the way. So okay, so we are in this situation where we're analyzing the physics of a scalar shield that looks like it is in flat space, except for the fact that its mass is time dependent. Okay, we'll come back to that in a second. That dependence of the mass on time means that, as I wrote, that the energy is not conserved, and on the quantum side, that the particle number associated with the quanta of these fluctuations is not conserved. Okay, so you can start in a state with no delta chi, and just by time evolution end up in a state with a non-zero number of delta chi particles. So, but let's see that in a second. We at the moment we have an action which is quadratic for a scalar field. We can find its equations of motion and look at its at the solution. So the equations of motion that follow from S of delta chi are the following. Again, primes denoting derivatives with respect to conformal time. So chi prime. Prime is the second derivative, Laplacian of chi plus m squared a squared minus a double prime over a chi equals 0. Let me just check something. Yeah, that's correct. Then, as ever, because chi depends on tau and x, we have this term here, which is in general non-zero, the Laplacian, and the usual way to try to solve this is to go to Fourier space. So in Fourier space, we can expand a certain perturbation or certain field profile x into Fourier mode. So this is the integral. With my conventions, this is going to be 3/2. And then there is chi of k vector tau e to the I k dot x. So this is an ansatz that we can plug into the equation of motion and then get a differential equation, a second order, because this is second order here and here, a second order differential equation for these coefficients here, okay, which we will see are related to what are called the mode functions. So these coefficients or these functions here solve the following equation: chi double prime of k. Now the spatial derivatives pull out factors of ik, so there's two of them. So this is plus k squared chi plus, just for short, m effective squared chi k equals 0. Okay, this is a second order ordinary differential equation for the function chi of k tau. And this is going to have two linearly independent solutions, which we can write as follows. some integration constant times one of the solutions plus another integration constant with a minus k and a k here times a function of tau here and k. Okay, you have to keep in mind that these things appear in such a way because chi is a real scalar field. Okay, so chi is a real scalar. So when you take the complex conjugate, chi needs to go back into itself, and so you have to just write the solution in such a way. So these a's, I'm running out of space here, but these a's are integration constants, and the v's are the mode functions. So v are the mode functions. In particular, they're mode functions if they are obey the following normalization condition. The imaginary part of v prime times v star equals 1/2. It's just this ensures that they are linearly independent. So this is the classical story. Okay? But what we want is to understand the origin, ultimately, of this. Okay? And the origin of this in the classical part of the story comes from these integration constants. Okay, so these integration constants are what tell us what is the profile of the perturbations, which ultimately leads to the CMB once you do things properly. So, because we expect inflation to happen at high energies, and there are two motivations to do what I'm about to do. On the one hand, we expect inflation to happen at high energies. We don't know how high, and we haven't explained how the energy of inflation, the energy scale of inflation falls out of this. But we expect it to happen before the Big Bang, and the Big Bang being close to this initial singularity, we expect it to be a moment of very high energy densities. And on the other hand, we also expect, and this is some theoretical bias, but it has worked so far pretty well. We also expect the classical world to emerge as a suitable limit of quantum mechanics or of quantum field theory. Okay, so this allows me to say, okay, now let me just study this system that looks like a scalar field in flat space. Let me study it as a quantum system in the early universe. Okay, and what we're doing is essentially can be called, with a bit of a stretch of the words, quantum gravity. We're doing quantum effects in gravity, and hence the title of Mukhanov's book. We're not quantizing gravity per se. We're dealing with a classical gravitational background on top of which we have quantized perturbations. Okay, and this is fairly solid. It's been known from a technical side. It's been known for 40 years or 50 years, and there's nothing so exotic about it, even though at times it can be a little bit technically challenging. So we want to quantize these scalar perturbations. And I repeat, we're not doing full quantum gravity. The metric is classical. The geometry is classical. It's just GR. What we're doing is we're doing QFT on a curved background. And the curvature of the background changes things, makes them more interesting than what you usually learn in QFT1 or QFT2 or whatever. Okay? And we can do this in a number of ways, but perhaps the most easy way to approach this is to canonically quantize the scalar field. Okay? So we're going to canonically quantize chi. Okay, and by this I mean we're going to follow the Hamiltonian approach to analytic mechanics, and we're going to substitute where we have the Poisson brackets in analytic mechanics, we're going to substitute that by the commutator promoting phase space variables to operators over a Hilbert space or over a Fock space. Okay, so this is just how you usually do in QFT1, and it's the simplest case because this is a scalar. So in order to canonically quantize, we first need to define the canonical momentum. And the canonical momentum is just the derivative of the Lagrangian with respect to the generalized velocity. And because the Lagrangian, if you go back, is just chi prime squared over 2, this is just chi prime. Okay, so this is the canonical momentum. And what we're going to do is promote chi to an operator, so a function. On the left-hand side of this arrow, we have functions on phase space. On the right-hand side, we have operators on Hilbert space. Sorry, this is not a prime, this is just a hat. And so we promote the same thing, we do the same thing with the canonical momentum. And where we had Poisson brackets, we change this to commutator over I times h bar. This is the recipe given to us by Dirac, how to find the quantum system when we know the classical system. So this is the first quantization prescription. And if we do so, we can see the following equal time commutation relations. Okay, equal time here is important for the operators chi and pi. So from the fundamental Poisson bracket, we deduce, following Dirac's prescription, that the equal time, so this is the same tau, the equal time commutator is just I times the delta function of x minus, this is a y, sorry, just not clear, x minus y, and all others are 0. So if you compute the commutator between this and itself, but at a different point in space, this is equal to the same thing with pi, x tau, pi, y tau, and this is 0. Okay? Now, if we go back a second, so when we're doing this, these are operators over the Fock space of the theory. Before, we had the solution for the chi's written in such a way. Okay, so when we quantize, this was a classical solution. There was no quantum arguments anywhere in this. We had an action, we found equations of motion, and we found the solutions to this differential equation that is the equation of motion. Now, when we quantize, what happens is that these integration constants, this a minus and a plus, get promoted to creation and annihilation operators. So the integration constants go into creation a dagger hat k and annihilation a hat minus k operators. Okay, and you can show, and this is another exercise you can do, that these imply that these have the usual So this is K vectorial prime here. These have the usual commutation relations for a harmonic oscillator. And then all others vanish. So essentially, the quantum version of the perturbation is an infinite set of decoupled harmonic oscillators. Okay, so we have one harmonic oscillator for each K mode, but other than that, when we have to compute things, we need to integrate over K in order to have the physical quantities. But other than that, this is just an infinite number of copies of what you do in quantum mechanics when you quantize the harmonic oscillator using the algebraic method, which is, in other words, using the creation and annihilation operators rather than the Hermite polynomials and all that, and all those analytic formulae. So if we have, so this is the exercise. So if we have a set of creation and annihilation operators, we can define also, as we do in quantum theory, the vacuum of the theory. Okay, so the vacuum state is a crucial quantity, a crucial entity in any quantum theory, and it is defined as the state that is annihilated by the annihilation operator. So something that is projected out. So let's call it like this, V, because V were the mode functions associated with the operators A and A dagger. Okay, so this is the vacuum of the theory, is this zero V, and then we can build excited states from the vacuum. So the vacuum is, in some sense that we can make precise in a second, the minimal excitation state of the theory, and then we can build more excited states by acting on the vacuum with creation operators. So the Fock space can be obtained by acting on zero with creation operators. Okay, in particular, if we want a state with m particles with momentum k1, n particles with momentum k2, and so on, all I need to do is get my vacuum, which I'm calling 0v, and act on this guy with a creation operator that creates particles with momentum k2. And if I want n of them, I put n of these. And if I want m particles with momentum k1, I have to do this. Creation operator with momentum k1, want m of these, so I put m of these. And then there's just a normalization factor to keep up with conventions. So this is how you build the various states on your quantum theory. So this happens to work, and it's fairly straightforward, and it's completely time independent in flat space. Okay, so in flat space, if you have 10 quanta of phi with momentum k1 now, and you have no other interactions, you're just working at the level of the quadratic action as we are at this stage. If you look in 10 years, you will still have 10 particles. Okay, that's not going to change. The number of particles is conserved in flat space. There's nothing that is explicitly dependent on time. However, the story is much more subtle when you go into curved space-time precisely because of the time dependence of the mass. This means that energy is not conserved, and also that particle number is not conserved, but also that the notion of vacuum becomes time dependent. Okay, so the choice of mode functions and creation and annihilation operators does not fix the vacuum. Okay? There exist different bases. So you can describe the Hilbert space, which is the complex vector space. You can describe it as you can do in R2, R3, or whatever. You can describe it with different bases, okay? And that's essentially the same thing that we find here. So there exist different bases of the Hilbert space. And that is to say, different sets of creation and annihilation operators related to each other by coordinate transformations. Which in this context take the name of Bogoliubov transformations. And each one, so each basis, comes with its own vacuum. Okay? So there are different vacua. So there exist different vacua. And this issue is something that is not present in flat space. So if you have flat space and you take the vacuum to be the state that minimizes the energy, that state is time independent. Okay? And that gives you the right prescription for choosing the vacuum and then for doing quantum theory by exciting and so on that vacuum. So in flat space, when there is no gravity and as consequence no time or no explicit time dependence, the vacuum is the state that minimizes the energy of the system. Okay, and the energy of the system is the expectation value of the Hamiltonian. Okay, so let this be a state, so be the vacuum. So let 0 be the vacuum of the mode functions V. Okay. What we want to minimize is this. So this is the vacuum expectation value, just like in quantum mechanics. You have the bracket notation. The vacuum expectation value of a certain operator, which is the Hamiltonian. This usually has a special name, which is the energy of the system. And if you expand, so H is a function of V, A minus, and A plus operators. Okay, if you expand this and use the commutation relations and the properties of the vacuum, you can show, again, Mukhanov maybe for more details, well, certainly Mukhanov for more details, you can show that this integral is a delta function. This is not a sigma, it's a delta, where Ek is the energy in mode K, and that is given like so. Okay, so this works in flat space for a massless, so flat space plus massless scalar. Okay, now this is an expression that we can minimize. Okay, we can minimize Ek for a certain function. Okay, so if we assume that V of K can be written as a modulus and the phase, modulus alpha phase, modulus R phase alpha, we can express E, the energy, in terms of R and alpha, and we can minimizes E of K if V of K is 1 over root 2K e to the I k tau. Okay, and in which case, E of k is just k. So this is the mode function corresponding to the vacuum V that minimizes the energy in the case of a flat space massless scalar. There's no time dependence here, no explicit time dependence. K is just a wave vector, it's fixed. That's everything is fixed. Now, when we go into in the presence of gravity, we need to substitute k squared by essentially the frequency squared that we have, which you can read if you go back to the equations of motion. Where are they? By this, okay? So this is omega squared times chi k. Okay, so this is the definition of omega squared. So omega squared is k squared plus the effective mass squared. And this depends on time. So the functions that minimize the energy depend on omega. So here we're going to have an e to the I omega. So V of k is going to be proportional to e to the I omega k of tau times tau. So they depend on time. And by depending on time means that they will not be, so the vacuum is not going to be time independent. So the notion of vacuum is not time independent. Okay, and this fact is all due to the fact that the mass, the effective mass, is a function of time. Okay, so the vacuum at some time t0 is not the vacuum at some time t1 with t1 different from t0. So in the presence of gravity, we cannot talk about an absolute vacuum. What we have is an instantaneous, the best we can do is have an instantaneous vacuum. Okay? A state that minimizes the energy at a given time. But unlike the flat space case, where if you have 10 particles today, you're going to have 10 particles tomorrow, in the presence of gravity, if you have 10 particles today, you're not going to have 10 particles tomorrow. You can have more, you can have less, depending on how things are evolving. And all of this thing can be traced back to gravity and can be traced back to the time dependence of the mass, of the effective mass of the scalar. Now, I started talking about inflation. I've been talking for about an hour. And I haven't gone back to inflation. So this story needs to be applied to inflation. Okay, so in inflation, so this is fairly, these observations are general. I didn't say how the scale factor depended on time, what was the source of energy momentum, and so on. But we can render these observations more like sharper in the case of inflation. So if you have inflation, so for inflating or de Sitter backgrounds. So by de Sitter, I mean things that are essentially a constant, a cosmological constant. So the energy momentum tensor is just a pure cosmological constant, and this is often used as a first order approximation to an inflating background. It captures most, but not all, but most of the features of inflation. So in the Sitter backgrounds, we can show that the relation between scale factor, and you may have seen this before, the relation between the scale factor, the Hubble parameter, and the conformal time is as such. And in this situation, the effective mass, because the effective mass, let me remind you, dependent on the second derivative of the scale factor. So we can write this as AH squared M over H squared minus 2. And the time dependence is in this prefactor. And so in an inflating background, what we're going to want to do is to solve the equations, the second order differential equation for the mode functions, okay? Which looks in this case like so. Where I'm trading AH squared by 1 over tau squared because we're in this quasi de Sitter or de Sitter. And this tells me the behavior, so this fixes behavior of mode functions. Okay. Now, these mode functions, well, the solution to this is known. It's just a superposition of Hankel functions, but if you're like me, that doesn't tell you much. So you can just get asymptotic solutions to this and get a feel for the physics that's taking place. Okay, for the sake of this argument, let's just ignore this factor here. In inflationary models, this needs to be small anyway, so we're just going to set it to 0 for the time being. And we have essentially an effective mass, which is k squared minus tau squared, or minus 2 tau squared. Now, if k squared dominates, if k is much greater than AH, which is 1 over mod tau, then I can neglect this. I was covering this with my hand, but I forgot that you just see the red dot. So I can neglect this bit, okay? And I have essentially v double prime plus k squared times v. So we're going to have oscillating solutions. So the solutions are of the type some integration constant e to the I k dot tau, I k tau. Okay, so these are oscillating. If, on the other hand, k is much smaller than AH, that means that this term is going to dominate over this. Keep in mind that this is going to be set to 0 for this time being. Vk then has a power law. This is a constant of integration, which I call c minus 1 plus c2 tau squared. So the oscillating solutions are no longer present. What we have is a growing and a decaying mode. Okay? As I said, the exact solution of this is a superposition of Hankel functions with integration constants. So Hankel of type 1 minus k times tau plus c2 Hankel 2 nu minus k tau. Okay? But these are the solutions to the second order equation of motion. We haven't said anything about the quantum side of this theory. Okay? And that comes through the specification of the vacuum conditions. Okay? So the instantaneous vacuum in the Sitter or inflation backgrounds is the one that so this is easy to understand, forget about the maths for a moment, in terms of relative size of two length scales, okay? So when we have gravity, in particular during inflation, we have a length scale associated with the curvature of the background spacetime, which is given by h, okay, by the Hubble parameter. And now we're considering perturbations with a certain momentum k, which is associated with a wavelength which goes like lambda, which goes like 1 over k. Now, when lambda is very small in units of the background spacetime curvature, so in units of h, essentially these perturbations should live like in flat space. They don't feel gravity. Okay, there's a decoupling effect from the curvature of the background. So they live as if they were in flat space. And then in that limit, we need to recover these mode functions. Okay? That amounts to choosing. Okay, that amounts to choosing the integration constants. So the instantaneous vacuum in the sitter, which is called the Bunch-Davies vacuum, corresponds to choosing C2 equals 0, C1 equals 1. And you can see this easily if you just look in a book or you expand in Mathematica, the Hankel functions when x is much greater than 1, you get the mode functions in flat space. And you need to impose this condition. So as I was saying, if this is your Hubble horizon, which has a certain size, let's call it LH, which is 1 over h. If you have perturbations with a lambda physical, which is much smaller than the curvature of spacetime, these guys don't feel curvature, okay? On the other hand, if you have perturbations which have a lambda physical which is much greater than LH, then they will feel this, this curvature. Okay, so this is what's called the super horizon and the sub horizon limit of the perturbations. Now, if I have, yeah, I'm finishing now. So give me just a couple of minutes to try to connect to this. Okay. So what we have done is we have developed a mechanism or a formalism, let's say, to compute the perturbations of a scalar that is a quantum scalar on a curved background. Okay, and what we want is to see if this has any consequences for the universe, because we know that the universe is at first order homogeneous and isotropic with small tiny wrinkles superimposed onto this homogeneous and isotropic background. And what we want to do is to characterize these wrinkles with the assumption that their origin is quantum mechanical, okay? That these small perturbations originated from quantum mechanics in the early universe, okay? So we want to characterize the chi perturbations. Okay? We have solutions to the equations of motion. We have promoted them to quantum fields and the integration constants to operators. And we want to characterize the chi perturbations, in particular, want to characterize their statistics. And in the approximation that we're working on, which is at the quadratic level, the action for the field chi is quadratic. And so we are in a situation where the partition function is Gaussian. Okay, so we have a Gaussian partition function, and if we have a Gaussian distribution, we know that all the odd moments are 0 and all the even moments are completely fixed by the 2-point function. So we want to, it suffices to know the 2-point function or the power spectrum of chi. Okay? Because what we want is to know what's the average value of chi. Well, the average value of chi is 0 because this is Gaussian, but we want is essentially this. So this is encoded into the power spectrum of chi, which we are taking to assume a massless scalar in the sitter spacetime, just for simplicity's sake. And we want then to compute the 2-point function over the vacuum. So if there's no other source of anisotropy, and this is an assumption, there is an anisotropy that is generated by quantum effects. And this is what we're trying to characterize. by looking at the two-point function of these operators k and k prime. Okay, knowing that v hat of k is just the creation operator times the mode function. I'll be a little bit more explicit here because I'm also finishing. This is just mode function. So this annihilation operator mode function plus creation operator mode function conjugate times the same thing with k replaced by k prime. So v k prime plus a k prime v star of k prime sandwiched between the Bunch-Davies vacuum. And again, we can use the fact that the annihilation operator on the vacuum, so here I'm using this notation, is 0, and the complex conjugate is also 0, plus the commutation relation between A and A dagger to show that this is mod Vk squared times delta k plus k prime. And this is what's called the power spectrum. So if this is, well, I understand that this is going a little bit fast, perhaps, depending on the background that you have. And again, that's something I'm not entirely sure what the background level is. What we're trying to do in words is to say how big are the perturbations, okay? And this is mathematically characterized by this power spectrum. Now, because we have the mode functions, we can check that the power spectrum on superhorizon scales for the perturbations is a function of the wave mode, and this is AH squared over 2k cubed. Okay, and this is the quantity that with due care to work with the right gauge invariant variables and so on is related to the delta t over t bar. In particular, the relevant quantity that is fixed by this. So how do you analyze this, right? I mean, you have a sky map, you have 4 pi of data, and you have a finite number of pixels that obviously depend on the angular resolution of your camera. And what you do is essentially do a Fourier. Well, you expand this scalar field in spherical harmonics, and you just find the multipoles, and you characterize the two-point function by a scalar amplitude. Which for the right gauge invariant variable, which is not the chi's here, but are a close cousin of these chi's, from this data that you see on the screen, okay, you get a scalar power spectrum with an amplitude that is 2 times 10 to the minus 9. So this is the scalar power spectrum amplitude, which is nothing but this thing here rescaled by a factor of k cubed and with a little bit more care into using the right gauge invariant variables, which cancel this factor of a squared here and bring about a factor of of epsilon. So the variation. So let me just say, I'm not sure I said this in the beginning. Epsilon is just h dot over h squared. So this is what gives me the time variation of the Hubble parameter, and is supposed to be a small parameter during inflation. So this scalar power spectrum amplitude is measured. So let me just stress, this is measured, okay? This is measured. This is a number that is being stable, and it's from across a number of different generations of satellites. First with Kobe back in the early 90s, then onto the subsequent second and third generation experiments, WMAP, early 2000s, and then Planck, 2015 to 2019-ish. This number is measured. And what can we learn from this? I mean, this 2 times 10 to the minus 9 follows from this sort of sky map. And it's a window into the early universe because this is measured. And this is measured means that this following quantity is measured. And this is the energy scale in the early universe. Okay, so this is an extremely important measurement if you're someone interested in early universe physics, early universe cosmology, because it allows you a glimpse into what was the energy scale, something that you cannot get purely from studying inflation at the background level. Yes, it has its virtues, even at the background level. It explains the fine-tuning problems, but it does not tell you at what energy it happened, at what energy did inflation take place. And this is something that helps you to get there. It doesn't get you there all the way because AS depends on this particular combination of parameters, h squared over epsilon, not on h squared alone. But there's a similar relation for tensor modes, and that is gravitational waves from the early universe, okay, whose physics is very similar to also to what we've described here today, but there was no time for that. And AT is essentially proportional to h squared. So if you have primordial gravitational waves, if you have a measurement of this, then you know the energy scale of inflation. So inflation, just to sum up, because I'm over time, well over time, inflation not only explains the apparent fine-tuning of the early universe, it also gives you a mechanism through the quantum fluctuations of just a system of scalar field plus gravity. So the quantum fluctuations of this system give you the seeds for the anisotropy, for the small levels of the anisotropy that are observed in the universe at the level of the CMB. And these seeds, through gravitational collapse, are then the seeds that give rise to galaxies and clusters and all the gravitationally bound structures that form in the late universe. So I think this is all I wanted to say. I think that there might be questions, so I will stop here.
Thank you so much. I think we can turn off the